When I brought the security use cases to chaos engineering, he started saying, well, Aaron, I hadn't thought about it until you brought it to us at Netflix that system safety, there's two sides of that coin of system safety. There is security and availability.
Hi, you're listening to The Secure Developer. It is part of the My DevSecOps community, which also includes the upcoming free DevSecCon 24 virtual conference. With great speakers intersecting the dev and security worlds, it's not to be missed. Sign up at devseccon.com. This podcast is sponsored by Snyk. Snyk is a dev-first security company helping companies fix vulnerabilities in open source components and containers without slowing down development. To learn more, visit snyk.io. On today's episode, Guy Podjarny, president and co-founder of Snyk, talks to Aaron Rinehart. Aaron has been expanding the possibilities of chaos engineering in its application to other safety-critical portions of the IT domain, notably cybersecurity. He began pioneering the application of security and chaos engineering during his tenure as the chief security architect at the largest private healthcare company in the world, United Health Group. Rinehart recently founded a chaos engineering startup called Verica with Casey Rosenthal from Netflix, and is a frequent author, consultant, and speaker in the space.
Hello, everyone. Welcome back to The Secure Developer. Thanks for tuning back in. Today, we're going to dig into security chaos engineering, which is a topic we just scratched the surface on at a previous episode with Kelly. And to do that, we have really a top expert, I guess. You could say you wrote a book on it, or writing a book on it, which is Aaron Rinehart, who is the CTO and co-founder of Verica. Aaron, thanks for coming on the show.
Thanks for having me.
Before we dig in, we're going to go deep here, hopefully on, what security chaos engineering is and why it exists. But before that, tell us a little bit about what you do, maybe what Verica does a bit, and a bit of the journey that got you here.
So we are the creators of chaos engineering, where my co-founder is Casey Rosenthal. He created chaos engineering at Netflix, ran the teams, ran the traffic team, core team. I am most notably known as being the first to ever apply what they were doing at Netflix to cybersecurity. We wrote the first open source tool called Chaos Slinger when I was at United Health Group. At Verica, we believe we're building a series of tools that evolved off of the work both Casey and I did in chaos engineering. We classify our tools as continuous verification. But what we mean by that is that it's a series of tools that help people understand their own systems. Chaos engineering is one tool set within there, canaries, feature flags, observability tool sets, things that help people continuously verify that the system is what they think it is and it's operating as intended. That's really what we do.
So how did you get to this place of co-founding Verica? How did you get into security in the first place?
Well, I'll start with Verica. I co-founded Verica with Casey about a year and a half ago. We wanted to try to bring a more mature tool set to the space. The space lacks a lot of tooling, and we wanted to evolve both my work from United Health Group and his work at Netflix with CHAP and bring more sophisticated tools that can help people navigate these problems and complexity in modern software. Prior to that, I was the chief security architect at United Health Group. At the United Health Group, I was part of leading the DevOps transformation, did some work again in cloud transformation. It feels like every place I would go with cloud transformation. Actually, one of the main drivers of chaos engineering is cloud transformation. We'll cover that later. And I wrote the first open source tool that applied Netflix's chaos engineering to cybersecurity. That was Chaos Slinger. We can talk about that and its use cases if you're interested. But prior to that, I spent time working in the DoD, U.S. Department of Defense, Department of Homeland Security. I actually a stint of about 4 years at NASA working in safety and reliability engineering. So it's not too far of a stretch from resilience engineering. And I'm a former U.S. Marine. That's
interesting. Like you could kind of claim, you went from military to safety and kind of reliability to security to finding a merger of the two in security verification, I guess. And
in terms of career path, I started off in network engineering. And then I got into sort of more sysadmin, system engineering type of work. And then for some reason, couldn't get jobs doing that. So I got hired on as a PeopleSoft developer, and I became a database engineer. And then I started writing front-end code. Then I started writing web apps. And then I ended up being a software engineer for about 10 or 11 years. At NASA, I had the opportunity to get into security because nobody else wanted to do it. I remember the first time I ran Nessus, which is a scanning tool. I followed a tutorial on the internet, and I put the exact IP address that was in the tutorial, and I ended up scanning the German government from NASA. It was quite an interesting day.
But one way to get exposed to it.
That was my intro to security. That's why NASA's where I sort of got into security. And then I had a fairly accelerated career in cybersecurity, given the fact that I had such a wide engineering tool set. I was able to sort of sift through how things work and whether things were secure or not a lot quicker than other people because I was a builder most of my career. There's only so many ways to build and only so many ways to secure what you built, and that accelerated my ability.
That's actually like a great perspective on the advantage, I guess, of sort of going from engineering background and kind of maybe the wide variety of ways to build things into security and how that boosts you up. Let's dig into the substance, we've been promising. So before we go into security chaos engineering, can you give us a little bit of a primer to what chaos engineering is in the first place?
So chaos engineering is the idea of proactively introducing turbulent conditions into a distributed system to build confidence that the system operates the way you think it does, right? So the key thing with it is it's proactive, is that a lot of times we don't really know something's broken until it's broke, and you have to incur pain in order to know there's something wrong and to go back and fix it. What chaos engineering does allows us to introduce these turbulent conditions, these faults, these failures in the system proactively to try to surface failure proactively so we can fix it before it manifests into problems. And the process of doing that, you build confidence that the system works the way you think it does. And just a little context around chaos engineering is that I've asked this question of several other people in the chaos engineering space. I don't think anyone has ever seen a chaos engineering experiment, which is failure injections that we inject, succeed the first time. What that usually means is that you never do a chaos experiment you know is going to fail, right? Because if you know it's going to fail, just fix it because you already know it's not going to work. You're trying to ask the computer the question, hey, when X occurs, I designed Y to be the result, and is that happening, right? You instrument that. You're asking the computer a question. Very often we're wrong about how our systems work. It's not any engineer's particular fault. It's the fact that the size, scale, and complexity and speed that we're building things today is very difficult for humans to mentally model that behavior.
And I guess failures here vary. Is it mostly about virtually unplugging a network cable or sort of taking down the servers, or does it get fancier than that?
It can get a lot more fancier than that. Most open source tools you see out there are really focused on sort of the basic failures, similar to what Chaos Monkey did 11, 12 years ago. So it all began with Chaos Monkey and Netflix's story. Actually, here's something that I like to remind people of, is that chaos engineering came about during Netflix's cloud transformation from DVDs to Amazon streaming. I love it when people are like, oh, Aaron, we can't do the DevOps. We can't do the chaos engineering. We can't even do the DevOps. And like, we're just beginning our cloud transformation. It's like, whoa. That's exactly what Netflix used it for. So most people use chaos engineering for is that most cloud transformations, like, people underestimate the time it's going to take to do it. They complain they don't have the right skills or the right people. And if you hire Amazon to build it all for you, then they're worried about not having the competency understanding, and they way underestimate the resources needed and the cost, right? That's why chaos engineering was so valuable, is that as you were building, you're building out your applications, you're building whatever product or service for the business you're intending to build out there, you continuously verify and ask the application and what you built the question, hey, do you work the way you're supposed to? Do you work the way you're supposed to? And you create that feedback loop, right? You constantly create a feedback loop of, hey, yeah, what we're building is actually working. And it builds that confidence. It reinforces skill sets. And when it doesn't work, you're able to get context of maybe what wasn't exactly configured right or what needs to be fixed. Chaos engineering is really about putting well-defined problems in greater context in front of engineers. It turns out when you give engineers the greater context and better definition of problem, it's easier to solve those problems. And that's really kind of what it's about.
I'm a big fan of the chaos engineering concept and how it gives you a feedback loop in an intentional fashion, to sort of see what happens if. And it's great to sort of hear you, like I fully kind of relate to, this is applicable really kind of at any system. That said, when you think about when do you inject that failure, people are a little bit afraid of actually taking down their system. So I've injected this failure, right? I've pulled out this sort of virtual cable or severed some connections or some disk access, and my system will actually be down. How do you see, do people run chaos engineering primarily in production? I know Netflix today, at least, is kind of, very well known for cutting things off in production. Or is it something where most of the world is still doing this in kind of pipeline or staging surroundings?
There is, in the New O'Reilly book that just came out 3 weeks ago, I think there's a chaos maturity model in the book. I think it was written by Nora. I'm not sure if that was Nora Jones who wrote that or not. So you don't have to do chaos engineering production to get the value from it. I mean, ultimately, that's where the outage or the security incident or the breach is going to happen. We all know there's a drift between what's in stage and what's in prod. But you can learn a lot about your environment through stage. So I'm going to tell a brief story. It's not my story, it's Casey's story, but it was one of the first banks to ever do chaos engineering. Invited Casey out to do a tech talk on chaos engineering to the team, and they're going to do the first game day exercise. The game day exercise is actually a manual where a team gets in a room and they inject the failure, and then they observe it, and they observe whether or not they're right or wrong, whether the system worked the way they thought it did. And so in this case, they were going to bring down a Kafka node. They said, Casey, we're a bank, so we have real money on the line. We can't do this chaos engineering stuff in production. He's like, all right, outage is going to happen on production. Okay, sure. We'll do it on stage. So they went forth. They got everybody in the room. Casey had done his tech talk, and they're live doing this game day exercise. They go forth, and they bring down the Kafka node in stage. Can you tell me what happened?
Did production go down?
Production went down, right? But that illustrates the issue, right? Is that resilience is not something a system has, it's something a system does. And it's the humans that create the resilience in the system. In this case, with all the complexity, like I said, and speed and scale and how we're doing things, they just forgot to change the pointers information. It's a human thing. It happens, right? We should expect that kind of stuff is going to happen and have mechanisms to reassure ourselves that we're prepared when those kind of things happen. Think about this. There was no outage. There was no incident. Everybody who could bring Kafka back was in the room. I grew up on a farm in Missouri, so it's kind of like when you do a controlled burn of a field. It's like you don't just light a match and go to town. Like you get notified the county, you bring out the EMT, you have the fire department. Everybody's there in case something happens, right? That's when you do chaos engineering. And you're not freaking out because during an incident outage, people freak out, right? I mean, their cognitive load is consumed by, oh my God, this could be a breach. Or this CEO is on the phone telling me I got to get this thing back up and running, or somebody's going to lose their job over this. People are kind of just freaking out. And the focus is on get it back up and running, not fix the problem. It's get it back up and running, right? Because they're losing money probably, or the call center's getting overloaded. And that is not a learning environment you want to be learning in. What's always interesting is you see the most messed up changes happen during incidents that would never be approved outside of an incident scenario, right? It's like, whoa. You're changing that variable? Like you made me go through 6 weeks of change review to change that, and you don't even understand what you're changing, but you can change it during an incident. What happens is, because we do that, one problem will beget another problem. That's what you go from war room to war room to war room to incident to incident to outage to outage. Here's another brief story, then I promise I will shut up on this point, is that I was out at one of the largest financial payment processing companies. We're talking to this chief engineer. He was telling us about there's this legacy system that they depend on. The core company's application that makes us money runs on this thing. It's stable. It's known. The engineers are competent with it. It rarely has an outage. It's our legacy trusted system. Because they need to extend it for other capabilities and purposes, they want to move it over to Kubernetes, a very untested sort of platform for them, and they don't have confidence in it or skill set. I was a bystander in this conversation with Casey, this gentleman, and I was thinking about, I said, how does a system become stable? Is it stable from day one? At one point, that legacy stable system was probably just like a Kubernetes. It was unknown, untested. Our systems become stable through a series of unforeseen events. If we could have foreseen it, we would have just fixed it. These unforeseen outages and incidents informed us how the failures in our system that we needed to fix, but we encountered pain through our learning. With chaos engineering, you could think about it. I did a lot of writing on this particular envelope of knowledge, the Security Chaos Engineering Raleigh book that's coming out in the summer. How does your system become stable? Chaos engineering is a way to sort of accelerate that in a controlled and managed way. Is to proactively inject the conditions by which you expect your security to fire or to be triggered, and ensure that, it does actually work. Okay, it is working, right? It does catch the misconfiguration. It does catch an open port that shouldn't be open. It does catch a permissive account or a role collision. It does catch these things that we expected. Then what you do is you automate those tests and it becomes more of a regression kind of thing. Once you've proven that the experiment is successful.
Love it. And also love the passion, like very clearly, you talk about it, you're introducing failure, you're creating that feedback loop of understanding what if scenarios for that failure. So like chaos engineering has historically not been known for security application, right? It's been known as like an aspect of resilience, and initially its sort of tie into security has been more in that intersection of availability and security, so like denial of service or things like that. But I think when you talk about security chaos engineering, you're talking about broader applicability, right? So what's that slice of chaos engineering, or is it a slice or an adjacency that is security chaos engineering? What's different about that from chaos engineering?
So I would say Casey likes to say that when I brought the security use cases to chaos engineering, he started saying, well, Aaron, I hadn't thought about it until you brought it to us at Netflix, that system safety, there's two sides of that coin of system safety. There is security and availability. But the use cases are a little bit different. It's really the same technique. It's failure injection, it's fault injection. That's also what separates it from maybe like a red team or purple teaming or like BAS, breach and attack simulation tool sets. I can expand on those a little bit. I've tried to do that in the O'Reilly book, and I wrote an article on opensource.com called Red Fish, Blue Fish, Purple Fish, Chaos Fish that talks about the differences, just because I got that question all the time, all of which are valuable, by the way. Don't get it twisted. The more objective information we can derive about how our system functions, that's good. And red teaming, purple teaming, instrumentation is key. But so the use cases around security chaos engineering, really, this was all an experiment at United Health Group, right? My original use case was control validation. So people would come to me with hard engineering problems architecturally. I'd have a data architect and a solutions architect come to me with two different diagrams of the same system. The different diagrams represented was their own mental models of how they believe the system functioned. But holistically, that is really what the picture really was. So they provide these recommendations. You need a firewall here, you need this thing here, that thing here. Placement matters, configuration matters, how it's tuned. All these things matter. I never got to see that. It's not somebody who wants to just be an ivory tower architect to just say, give them advice that may not actually work. So what I wanted to do is sort of skip the line and ask the computer the question. Under these conditions, do you fire? Do you work? How I designed you to work? And that was really sort of the series of use cases we came up with were around architecture and control validation. Mostly what the security chaos engineering use cases are focused on is really misconfiguration. And misconfiguration is a result of not a human making an intentional mistake per se. It's more like the speed, scale, and complexity. It's easy to be out of sync or to not have an accurate depiction or understanding of what you're securing, what you're configuring, because that can change. It's very stateful. It's stateless. The way we approach security typically is a lot of times it's a state, and that state changes on a regular basis. If you look at a majority of, let's say, malicious code out there, a majority of malicious code is junk code. It really is. It needs some kind of majority. Now, there is a small percentage of it, 5, 6 to 10% at the highest of that sophisticated nation state kind of stuff. Good engineers were hired to do that. The majority of it is just junk. It's stuff that should never execute. If you read through if you go to like any of the AV sites or already malware, the sites where they'll break down the steps, there's usually some kind of low-hanging fruit that has to exist for the rest of it to execute, right? What security chaos experiments are really focused on is accidents and mistakes that engineers make when they're trying to build things. So we'll inject a misconfigured port, or we'll inject a permissive account. We inject the things by which we expect the security to fire. What we're trying to do is also detect when these kind of conditions happen, because we know they're going to happen because of, like I said, the speed, scale, and complexity. It's easy to lose track of what the system actually is. It's easy to make those mistakes. What we're doing is trying to proactively discover them before an adversary can.
So this makes a lot of sense, but I'm trying to clarify something. Is the security chaos engineering for security controls? Like, is it always around saying, hey, I have a security control here that's supposed to catch an open port, supposed to catch this misconfiguration, and what you're doing with the experiment is to see if the security control triggers? Is there another use case, right? Because when you think about weaknesses in the system, it could be that open port might imply some traffic flowing in, right? Or things of that nature. Is it mostly around that former? Is it first and foremost on testing your security controls?
Well, there's several use cases. The control validation is just one. The manual chaos experiments so it's not just the first time you run an experiment, not only looking to see what worked, but also what else might have worked. For example, when we first started running Chaos Slinger, which basically the main use case that we went with Chaos Slinger. It's an open source tool that we wrote. So we picked a use case that a software engineer, a network engineer, a system engineer, an executive could all understand, which was Port Slinger. Port Slinger basically introduced an unauthorized or misconfigured port. For some odd reason, it happens all the time still. And so for whatever reason, it could be that somebody filled out a ticket wrong, the software engineer didn't understand network flow. It could be for lots of reasons. It could be the engineer just made a mistake when they executed the change.
Yeah.
We started injecting misconfigured ports on our AWS instances. United Health Group had commercial and non-commercial software. We were very new to AWS as a company, and we started injecting misconfigured ports, and we expected our firewalls to immediately detect it and block it and to be a non-issue. And so what happened was that worked about 60% of the time. The firewalls we used caught it and blocked about 60% of the time. And we expected it, though, to work 100% of the time. So that's the first thing we learned, is that it was actually a configuration drift issue in how we were configuring things between commercial and non-commercial environments.
So it caught it in like 60% of the instances of the setups would have caught it, while the other 40% didn't.
Exactly.
Got it.
Or the instances we ran it on. It wasn't all of them, but it was interesting that occurred. So furthermore, what happened is our cloud-native commodity configuration management tool caught it and blocked it every time. Thing we're barely paying for, caught it and blocked it every time. So that was the second thing. The third thing we expected to happen was that the SOC would get notified of this event. From both of those tools should provide log data to a SIM. We didn't use a SIM. We had our own security special logging tool that we had built as a company, but that did detect it and correlate an event. That event was sent to the SOC. The SOC got the alert, but what the SOC couldn't tell was which AWS instance it came from. Remember, we were very new to AWS at the time. As an engineer, you can say, well, Aaron, you can map back the IP address to figure out which instance it came from and where it came from. Well, there's a thing called SNAT, right? SNAT will intentionally hide what the real IP address is. And you could spend 30 minutes to 3 hours trying to figure out where it is. And if that were an active incident, and let's say you have $1 million a minute to your downtime on that system, that's very expensive. But we never incurred that pain. There was no outage. There was no incident. We learned these things. I mean, all we had to do was add metadata and a pointer to the events, and then it was fixed.
Yeah.
And we learned all these things. It wasn't just the control that we validated. Well, we did validate it. We learned. We got context that we needed in order to fix it. We were able to look with a wider lens instead of a set of blinders on the problem because there was no outage. We weren't freaking out. There's no CEO asking for 15-minute updates.
Sounds powerful. Like you test the security control itself, you test the almost kind of the incident response. So even in the cases that something did trigger, did it go all the way? Did you get all the information to actually make that usable? Do you see, maybe it was back then or maybe today, maybe this comes back to your sort of, breach simulation attacks, but do you see a combination of some proactive activity? Would you simulate a bot while you reduced a security control or something of that nature? See what happens? Or are we veering outside the traditional definition of chaos engineering when we do?
I've talked to a lot of people about combining breach and attack simulation mostly and chaos engineering. They're just different techniques. We're actually injecting the failure. We're not simulating an attack. So you have to think about this. We're doing this most of the time on very large scale distributed systems. I mean, hundreds to thousands of microservices, right? When you start stepping through multiple attack points and you're sending a lot of data to the system, it becomes very difficult to sift through that data, what broke, what didn't, what worked, what didn't. And you have to account for the nonlinear nature of a complex system. Is that complex systems also can't be modeled. It can't be really diagrammed. Is the only way to understand a complex system is to interact with it. And if you start doing a bunch of things, it's very difficult to figure out what happened, what didn't. I mean, yes, you'll understand what happened to the initial target. But what about all the cascading issues? You lose that visibility because of all the noise.
And that drives you to sort of make the specific change as accurate as possible because you don't want to introduce additional complexity with like a very complicated experiment.
I've always tried to stay away from complicated multi-step experiments. You can actually learn a lot by one simple experiment, even just a port misconfiguration. Just doing that one experiment on all your instances, you'll learn a lot of different things. Actually, on the chaos experiments for availability, you can learn a lot. I mean, just about almost everything you need to learn through manipulating latency. You can learn a lot of different things about cascading failures, about like SLOs, SLIs, learn a lot of different things. I mean, some of the other use cases that I like to preach on for chaos engineering for security is, like you said, incident response. So incident response it's great for incident response teams. My boss, when we first showed him Chaos Slinger, he's like, Aaron, I love how this validates what we're doing on the engineering front. But Aaron, I love how this keeps my incident response team sharp. It keeps them well practiced. What you're able to do is, because security incidents are very subjective in nature. No matter how much you spend, how many people you have, you still don't know where it's coming from, who's going to do it, why they're doing it. When the event occurs, that may not have been when the actual incident began. That's just when you detected it. But with Chaos Engineer, we're able actually to kick off, to initiate the event. So we know what started, where the incident began.
You would mark as though there was, some unauthorized access to some system or something like that. Would that be the incident in this case, and sort of see what happens next?
You can go back to that port slinger example, right? We injected that. We can see whether the controls worked. We can see whether or not, we didn't have enough people available, or we didn't have the right skills, or the run books were wrong, or we're able to just look at things differently. One, because there isn't an outage. We're not trying to evaluate people during a high cognitive load situation. We're able to proactively discover these things in a way where the incident response team can learn. You can actually now manage and measure because you know the point at which it started. Your measurement's going to be very subjective if you're assuming that when you caught it was when the event began, because it's probably already too late because that's just when you caught it. And you're also assuming it wasn't a cascading failure that caused that. It typically is not one thing. It's simply multiple things that are parties to an event.
That's another statement that is true for reliability and for security itself. This has been a great overview of chaos engineering and the purpose of it, the notion of you don't actually have to sort of run this in production to get value of it. That's probably the eventual place you might aim for, but it doesn't have to start there. And for security, you can test the different security controls. You can test the sort of the incident response process for it and see how that works. If somebody wants to dig in some more and learn more, you've actually kind of written a couple of books or have participated in one and written another recently. So point us there again. What were the two names of the books to look up?
About 3 weeks ago, we released the official O'Reilly Animal book on chaos engineering. So there's a chapter about security chaos engineering in there. Actually, on the Verica website, I think it's Verica, verica.io/book. You can sign up there with a chance to get a free copy of the book. Other than that, at the end of the summer, Kelly Shortridge, who was on the show just before me, and I have been writing O'Reilly book on the topic. We've got several companies that have been involved that are doing chaos engineering, a lot of interesting use cases about container security, cloud security, how people are using it, how chaos engineering for security can be used to increase better logging, better monitoring, better observability. We expand on the use cases, and different companies give their stories as well. That'd be a great thing to check out.
That's awesome. Yeah, definitely. We'll post, I guess the first one, there's a link that we can post on the show notes. The other one, we'll have to sort of wait for end of summer to have that come out. One last thing that you can kind of be a guest on this show and not share. Beyond the security chaos engineering, which is the obvious tip that we've sort of spoken about, throughout the episode. If you have one bit of advice to give a team looking to level up their security prowess, what would that be?
I guess if I had to pick one thing, it would be that everyone on the security team must understand how to code. It's extremely valuable when somebody can go from idea to product on their own. And Python was originally written for children. Python's like Blizzard's theme, Blizzard Games theme, which is it's easy to play but hard to master. There's so many great things you can do if you know how to understand how to code, you now have a road to empathy, to understanding how software is built, and the challenges and complexity with it. It also helps you understand what SNCC does with software dependencies. You start to understand how those are really kind of a thing. This is kind of a supply chain problem, right? Then you start understanding, we don't have a lot of log events are not being written. We're blind to a lot of things. Understanding software begins, from my perspective, on learning how to code. And when you start to understand that, you start to understand how the sauce is made. And that really helps you open your eyes to pathways to better security and pathways also into the value chain. So if you're a security professional and you don't know where you stand in terms of the value chain of the company, you really need to think hard about that, because if you're not contributing to the value the company delivers, how long do you think your job's going to be secure? Mm-hmm. There's a way to do that. So
this is a great bit of advice, sort of definitely everybody in the security field. Aaron, this has been a pleasure. Thanks a lot for coming onto the show.
Hey, thanks for having me.
And thanks everybody. And I hope you join us for the next one.
Thanks for listening to The Secure Developer. That's all we have time for today. For additional episodes and full transcriptions, visit mydevsecops.io. If you'd like to be a guest on the show or get involved with the community, you can also find us on Twitter at @mydevsecops. Don't forget to leave us a review on iTunes if you enjoyed today's episode. Bye for now.